Welcome to another recording by Meston Educational Services. This video focuses on finding the derivatives of polynomial, rational, and power functions. So what you see on the screen, today we are doing derivatives of functions, and the two types of functions we will specifically look at is the polynomial functions and the power functions. And if you look at the expression that I've got for polynomial, it says a times x to the power of n. So a is the coefficient and n is the power. And for polynomial functions, n can take values like 1, 2, 3, 4, 5. So those are natural numbers. N could be 0 as well, but then the polynomial would just be a constant, which would be a. Now before I can go any further, I must state that the derivative of a constant term is always 0. So the derivative of 2 would be 0. Then the next bit we will be looking at will be power functions, which is nothing but an extension of the polynomial function. So the power would be m over n. So that's a rational power. Now m could be greater than n or m could be smaller than n. It does not make any difference when we are finding the derivative. The derivative rule would still be the same. The other kind of power functions we could be talking of is a hyperbola function or a truncus function. So that's x to the power of -1 or -2. So those are the ones that we are going to look at today. So finding the derivative of a polynomial function, there are two stages that are involved. So we are finding the derivative of x to the power of n. Now you will see the notation. I've got dy over dx. So dy represents the change in y and dx represents the change in x. And the change in x, we use the dx notation when dx approaches 0. So anyway, that's the calculus notation. So my function is x to the power of n. Now when I'm finding the derivative, the first step is you take the power, the original power, which is n, and you multiply the function with n. And then the second step is, in a derivative, you always reduce or decrease the power by 1. That's why I've got n minus 1. So these are the two essential steps. Whether it is a polynomial function or a power function, that logic would always hold. So let's look at an example now. So I've got derivative of x to the power of 7. So 7 is the power. So I take that power and put it in front, and I've highlighted that in red color. And then it's x to the power of the original power minus 1, which is 7 minus 1, which changes to 6. So the derivative is 7 times x to the power of 6. So that's pretty straightforward. This one is similar, but this one has a coefficient. Now when we are finding the derivative, a lot of people just leave the coefficient inside. It does not make any difference to the final answer, but I prefer and recommend that we first take the coefficient out. So we are finding the derivative of 6 times x to the power of 7. So I've taken the coefficient of 6 outside, and then I'm just finding the derivative of x to the power of 7. And now you can see 7 will come outside to multiply the function. So it's 6, which was the original coefficient, times 7, which is the power, into x to the power of 7 minus 1, and which simplifies to 6 times 7, 42, into x to the power of 6. So it is helpful to take the coefficient out, especially when it is a rational number or if it's a square root and so on. So we don't want to mix it up with the other numbers. So another example, 6 to the power 6 over 11 is a coefficient. So I have taken that out in the first step. So in effect, what I'm doing is I'm finding the derivative of x to the power of 3 over 2. And if I can find the derivative of x to the power of 3 over 2 and multiply that by 6 over 11, that will give me the final derivative. So 3 over 2 is the power. I bring that in front. So 3 over 2 times x into 3 over 2, which is my original power, minus 1. And that should give me x to the power of half. Now x to the power of half can be written under the root sign, and then 6 times 3 is 18, divided by 2 is 9, so that's 9, and then 11, so 9 over 11. So that's just the simplification part. So it's always advisable to write the derivative in the root notation if you can, or using the surd form, but it is not expected that you should do that. This one here, we are finding the derivative of 3 square root of x. Once again, 3 is the coefficient. I've taken that outside. Because we are working in terms of power, so root x I've written as x to the power of half. So eventually what we'll be doing will be half minus 1 would be the power, and we multiply 3 by half. So I get 3 over 2 times x to the power of negative half. Now x to the power of negative half, I've written that as the root sign, and I put it in the denominator because I've got a negative sign in front. So my final derivative is 3 over 2 root x as a fraction. So I've got a question, and the question part is on the red. It says find the derivative of that. Now you'll see I'm using the other notation, the function notation, to find the derivative. So f dash or f prime x represents the derivative. So I've taken the 3 out for the first term, and likewise I've taken the 4 out for the second term. So in effect, I'm finding the derivative of root x in the first part and derivative of 1 over root x. And then you can see the steps, and my final derivative you can see on the screen. So it's just the simplifying that probably you have to be careful with. So I've got plus 4 into negative half, and that's going to be minus. So that's why I've got minus over there in the final answer. So far we have looked at finding the derivative. We can also be asked to find the derivative at any given point. In the same question, I could have said find the derivative at x equals 2. So once you have found the derivative in your expression for the derivative, you'll go and substitute for x as 2. So we'll be looking at some examples. We'll be finding the derivative at a point. So this question has got a few parts. It's a very simple question to start with. It says the function is 4x squared minus 3x, and it says find the derivative at 5. So that means x is 5. So the first thing I obviously will have to do is to find the derivative, and then it's got another part over here. It says write the equation of the tangent at the x value for the function is 5. So it's got 3 things that we have to do. First find the derivative, then find the derivative at 5, and then find the equation of the tangent. So the derivative would be simply I multiply 4 by 2 and then reduce the power, which would be 8x minus 3. So that's the derivative. Now the derivative at 5, instead of x, you will see I've substituted 5 in place of x. So it's going to be 8 times 5 minus 3, which is 40 minus 3. So the derivative at 5 is 37. Now if you recollect, that is giving me the gradient. So now I know the gradient for the tangent is 37, and I'll be using that later on. What I also need is the function value at 5. So I'm going to substitute 5 in the original function, which is 4x squared minus 3x. So if I substitute that, 5 squared is 25 times 4 is 100, minus 3 times 5 is 15. So 100 minus 15 gives me the function value at 5 as 85. Now we know that to write the equation for a straight line or for a tangent, we go y minus y1. So y1 is the y value when we know the x value. So once we substitute, so it's going to be y minus 85, because that's the function value, equals m, which is 37, minus x1 is 5. And when I substitute the values and then I simplify, it gives me y equals 37 x minus 100. So that's the equation of the tangent at x equals 5. Now if you have your CAS handy, I would like you to actually try this on your CAS. So now to get to the derivative template, okay, if you can all add a calculator page, and then I'll just slow down over here. So if you add a calculator page, and then if you click menu, and you will see an option calculus. So I'll just show you here. Number 4 is calculus, and under calculus, the first option is derivative. The second option is derivative at a point, and then the 9th option is finding the tangent line. So these 3 are the ones that we are going to use. Now there is actually a shortcut to get to the derivative template straight away, and the shortcut is if you press the shift key on your calculator without pressing menu, shift key and then the minus key. Now why minus? Because the power decreases. So if I was to use this logic when I'm finding the antiderivative, the template can straight away come up by pressing the shift key and plus. So the shortcut for your CAS to find the derivative is shift and minus. Okay, so if you have inserted the derivative template, now the way you would enter it is you enter the expression in the bracket. So I've got d over dx of 4x squared minus 3x, and that gives me the derivative on CAS. Now to get the derivative at a point 5, if you go back to calculus, which was number 4, and then you insert the template for derivative at a point, now it will actually open up a template and it will say what's the point, and you will type in x equals 5. So you don't have to type in x equals 5, you just type in 5 in the template, and then insert the expression once you click enter, and that gives me the derivative at 5 is 37. So I'll wait for you all to try it. Probably I'll give you a minute or something, and then I'll talk about finding the tangent. Now, if you were to find the function value at 5, which I've done, so my expression was 4x squared minus 3x, and I'm substituting x equal to 5. Now to substitute, I'm using the condition or the when line, and you would on your calculator find this vertical line. If you press the equal to key with the control button, you will see the vertical line, and then all you need to do is substitute x as 5. So if you do vertical line and then x equals 5, that will give you the function value at 5, which is 85. Now the last part, once again, if you click menu, go to option 4 in calculus, and I have typed in the letter y just because I want to see my equation in the form of y. But if you don't put in y, it will just put the equation for the tangent line without y. So it's handy to just put y equals and then put the expression tangent line. The first part is the expression, which is 4x squared minus 3x, and you have to put comma x. Don't forget to put comma x. And then where are we finding the tangent? And we are finding the tangent at 5. So you do x comma 5. And then it gives me y equals 37x minus 100. Now, if I hadn't put y in front, the answer I would get would be 37x minus 100, which is fine as well. So it gives the answer in the form mx plus c. Now, this is just something we don't probably worry about much, but if I'm finding the derivative of 3x to the power of 5 plus 11x cubed minus 11x, mathematically what we are doing is we are finding the derivative of each one of them individually. So that's what I have represented over here, and this here is referred to as differentiation in parts. So we are finding the derivative of 3x to the power of 5, then we are finding the derivative of 11x cubed, and so on. So I've just illustrated that with an example. And the last one is derivative of 12, which is 0, so we don't need to write that. So the derivative of a constant will always be 0. Now this is an important concept that I'm talking about. Here it says the derivative at endpoints of a function is always undefined, and the reason for that is when we are finding the derivative, we are trying to approach a certain point and we are making the secant a tangent. So we can approach it from at the endpoints, we can only approach it from one side, we can't approach it from the other side. So a derivative exists only when we can approach a point from the left hand side and also from the right hand side. But if a function has endpoints, we can't approach it from either the left or from the right. So the derivative does not exist at the endpoints. So you will see I've defined a function which is x squared minus 5x plus 6, and I've actually restricted the domain. So the domain is -3. Which is a part of the function, because it says -3 is less than equal to x, which is less than equal to 4. But when I find the derivative, and I would like you to actually try that on your calculator, it gives you the derivative as 2x minus 5. But do you see it has changed the domain for the derivative? Less than equal to is not there anymore. So it says the derivative exists between -3 to 4, and -3 and 4 are not included. So it's just the less than sign and not the less than equal to sign anymore. So just observe how the domain has changed. So I can find the derivative at x equals 3 because 3 is very much within the domain, and the derivative at x equals 3 is 1. But you'll see if I find the derivative at the end point, when I put x as -3, my calculator displays undefined. And if I put x equals 4, which is the extreme right endpoint, the calculator will also display undefined. So what this confirms is that the derivative at the endpoint of a function is never defined. So I would like you to try this on your calculator. You can put any function. So for that matter, actually, I'll give you a square root function here where the domain is determined automatically. So we've got a square root function x minus 7. And we are finding the derivative at x equals 7 because the function starts from 7 and the domain is from 7 to infinity. 7 is included, but when we find the derivative, it says undefined. So just be careful with that. The derivative does not exist at the endpoints. So you can actually try any function. And now the question would be, if the endpoint is negative infinity and infinity, then in that case it's anyway never included because infinity is not a number, it's approaching an infinite number. So when we write the domain, we always use the regular bracket and not the square bracket. So the derivative also would be from negative infinity to infinity. Okay. Now you will see I've used a slightly different notation over here when I'm trying to find the derivative at two given points. So it says find the derivative at 0 and find the derivative at 2. So when I have 2 points, then I need to put them in the list form. Okay, and the question says then write the equation of the tangent at 21. So when x is 21, so the function value is 21. In other words, we are finding the derivative at 21. We'll have to find that as well. Let's first find the derivative. So 4x minus 3 to the power of half, and if I find the derivative, you can see it is 2 over 4x minus 3. So that's my derivative, and we can obviously go and check that on the CAS. Now because the function does not exist at 0, so if 0 is not defined, therefore the derivative also will not be defined. So that's not in the domain. So I intentionally put that because it's not in the domain. So at times what people may do is go and sub in the value and then say, oh, it's not simplifying or whatever. But in this particular case, because it's not a part of the domain, so the derivative obviously will not exist. But then my second point is 2. So in the derivative, I go and put x as 2, which simplifies to 2 over root 5. Now in your exam, you can leave your answer as 2 over root 5, but if you rationalize the denominator, then it will go as 2 root 5 divided by 5. It's again a matter of time. If you have the time, you can rationalize it, but you will not lose marks in the exam if you do not rationalize the denominator. Unless the question says write the answer in this given form, then of course you may have to rationalize. So there have been questions in the exams where it says express your answer in a certain form, and then you have to kind of rationalize the denominator. Now in saying so, every single year, if you take examination 1, the very first question is always finding the derivative, and the question generally is finding the derivative by either using the chain rule, the product rule, or the quotient rule. So these three rules are very important that you understand these rules. But to understand these rules, obviously you need to be able to find the general derivative and also need to know certain standard derivatives. So I'll bring up a screen with standard derivatives right at the end of this lesson. So coming back to writing the equation for the tangent, we are writing the equation for the tangent when the x value is 21. Now I need to know the function value at 21 and I need to know the derivative at 21. So the derivative at 21 is what we just, we haven't found that, but we need to find the derivative at 21. So the function value at 21 is 4x minus 3. So I put x as 21, which makes it 84. 84 minus 3 is 81. So the square root of 81 is 9. Okay. The next step, I've got the derivative at 21, and that equates to 2 over 9, or simplifies to 2 over 9, because it's really 2 over the function that was my derivative, so 2 over 9. So now I'll go y minus y1 equals m into x minus x1. So the value of m is 2/9, x1 is 21, and the function value at 21 is 9, so which becomes y1. So y minus 9 equals 2/9 within brackets x minus 21. And then of course I do my simplification. Now you'll see I've got my answer simplified. There's a red text box and also a black one. The black one would be probably a better form to leave your answer in, but if you wanted to take 1 on 3 as a common factor, you could do that, but I would be more inclined to leave my answer in the black text box form. So if you were to do this on the CAS, so the derivative of 4x minus 3, you can see that's under the root sign. So it's effectively, if you notice, it is 2 over 4x minus 3. So what would be the derivative if I was to ask you now of 8x minus 7? It would be 2 over root of 8x minus 7. So you'll actually see a very simple logic for finding the derivative of square root function. So it will always be 2 over, unless of course I go and put a coefficient in front, then it would change. And we are just testing, does the derivative exist at 0? We obviously knew it was not a part of the domain, so it's a non-real result. So the calculator will say, it won't say undefined, but it will give you a non-real result in this case because the function itself is not defined in that domain. Then the derivative at 2 is in the rationalized denominator form. So that's what the CAS does. And then finally writing the equation for the tangent line, I go and enter the expression. So 4x minus 3 under the root sign, and then I have to put comma x, and then I'm finding the tangent at 21, and then it gives me the expression. So at times you may find the answer that looks very different to what the calculator is displaying. So one of the things that we expect you to do is to compare and see if they are equivalent. So the calculator does actually allow you to enter your answer and the calculator answer and equate the two. If you put equal to, and if it says true, that means it's fine, your answer is fine. So at times you may have to just use your CAS to confirm whether your answer and the CAS answer are similar or same. Okay, derivative of other functions now, and these are the ones I was telling you that you need to be knowing. And when I go to the chain rule questions, I'll talk about that. But the derivative of sine x is always cos x. Then the derivative for cos x is negative sine x. The derivative of tan of x is 1 over cos square x. Now, how would you find the derivative of tan x? We will be using the quotient rule because tan x is sine divided by cos. So we will be using the quotient rule to find the derivative of tan x. But today I'm saying that the derivative is 1 over cos square x. Now in the methods course, you are okay to write the answer is 1 over cos square x. But if in your exam you wrote that as secant square x as well, that's fine because 1 over cos is secant. You are happy, we are more than happy to accept the answer in any of those forms. All these derivatives that I'm displaying on the screen would be obtained using the chain rule. So I would k times x, so the derivative would be k cos of k times x, and then cos kx would be negative k sine kx, and tan would be k over cos or k times secant. And what if it is this sine of x over k, then it's going to be cos kx divided by k, and obviously the same pattern would repeat for sine and. So all these will be obtained using the chain rule. This one is an interesting one, the derivative of Euler's number to the power of x. Now actually I did give this as a derivative curve yesterday, and you would have noticed that the derivative is actually unchanged. So the derivative of e to the power of x is still e to the power of x. However, the derivative of e to the power of k times x, the k would come in front and it will go e to the power of kx. So you just multiply the original function by whatever the value of k is. And the last one on the screen is the derivative of log base e x, which will be 1 over x. Now 1 over x actually is a rectangular hyperbola. Doesn't matter what the base is, but in this case base e. If you do the derivative curve, you will actually get a hyperbola. But we also know that log for negative numbers cannot exist. So log of -2 is undefined. And you will see at times I may use the absolute notation. When I use the absolute notation in my answer, it means that it cannot be negative. So at times you'll see the derivative written as absolute 1 over x. Now, if you're doing specialist, it will probably make more sense. But for the methods course, it is acceptable that you just leave the answer as 1 over x without the absolute notation. So we don't have to worry about that. So the first two are repeats. The last one, what if it is e to the power of x divided by k? So the derivative would be e to the power of x divided by k, and this time you multiply it by 1 over k. So multiplying by 1 over k means k becomes the denominator. So the derivative of log of kx is also 1 over x. So the derivative of, now when I use the ln notation, ln stands for base e, log base e. Now, when you are doing your examination, it is better to write log base e rather than the ln notation, because the exam will actually use the log base e notation rather than ln. I've just used ln, but in your writing, make sure that you use log base e. So what do you observe? Irrespective of what the coefficient of x is, the derivative will always be 1 over x, and that's why I've written important. So if you do k times x, or you do x times 1 over k, or x divided by k, the derivative is the same. However, if there's a horizontal translation, then the derivative would be 1 over x minus whatever the translation is. So 1 over x minus a. So that's the derivative with log functions. All these derivatives, as I said, we will be looking at them. What we would be doing is using the chain rule, which would be lesson 3. I just want to bring up some other derivatives that probably don't get asked as often, but it is still important that we know these. So the derivative of 2 to the power of x. Now all of them, you will notice actually the calculator gives the answer in the log form. So it will go, whatever the base is, it will go log base e to the base was 2 times 2x. So if it is derivative of a to the power of x, it will still be a to the power of x, but it will be multiplied by log base e of log of a. So the base will be e. So just remember those two. And using this, actually I can verify y is the derivative of e to the power of x 1 over, the log of x is 1 over x. We can do that. So if I look at the next one, derivative of log of x to base 10, once again it says it wants to go into log of e to base 10. And if I look at the last example, instead of base 10, I've got base a. So you can actually draw a parallel there as well. So it's always going to be log of e to whatever the base is divided by x. Now I've just written over there, for the last three, the calculator gives a domain warning. So you can just ignore the domain warning on the calculator. These are some of the examples that I have done, and it shows the working and the solution. And then if I keep going, it's got at some places it will say using the chain rule, and just some worked examples. So here it says homework, and it says determine the derivative for each of the functions underneath, state the domain for each of the functions, state the domain of the derivative for each of the functions, determine the derivative at 3 points. So when x is -3, x is 2, and x is 5. So you need to be able to determine the derivative for each one of them. And then for each one of them, write the equation for the tangent when x equals 2. And I've just got a warning over there. The CAS answer display may appear different from the answer that you may have obtained. So make sure that your answer and the CAS answer are equivalent. You could check it on the CAS by just putting your answer and the CAS answer and use the equal to sign, and it may say true. If it says false, that means you have an error in your answer. So I've got 1, 2, 3, 4, 5, 6 functions.